At least you're gonna have, the break though. Well, I'm guessing you're done too, right? Unless you have another exam today. Well, the memo is due on the 29th. I'll talk about that too. We got a while. Okay, so we'll get started. I'm recording, right? Yeah. Okay. Okay, so yeah, we'll get started. So, your memo, the fifth memo, I'm sure everyone saw the email by now, but you got to do that data reduction on your own this time around. So, the fifth lab, that's going to be due on the 29th of November. So I'm giving you more time to work on this memo because you're doing the data reduction on your own this time. Okay, so just double checking. It's the 29th. Okay. So basically, once you start working on it, I want you to kind of try to do it by yourself first, using your own kind of method, and hopefully you can do it all by yourself using whatever coding method that that you're doing by yourself. But if you can't figure it out, you can look at the deliverables handout. And at the very end, I have a kind of like a recommended attack plan for what to do. Where am I going? Deliverables. Okay, so yeah, there's a recommended kind of attack plan at the end of the deliverables handout. So you could take a look at that. But again, just I would recommend, only look at this if you can't figure out how to solve everything on your own. So at the very end of the deliverables handout, I have this figure here. I think this is from my 8:30 a.m. class on Friday, so your graphs are going to look a little bit different, but you should see something that looks pretty similar to this. And yeah, so basically what I did, I used two for loops, so I used a nested for loop. So in my first for loop, I'm looping through for the different stations, the left station and the right station. And then in a nested for loop, I'm looping through the three different materials that we have. And then basically, we got to make a vector for the transition impact energy that we have. So if we're looking at, let's say, like this blue curve here, that transition energy is maybe, I don't know, around, let's say, 70 foot-pounds, something like that, and maybe like 60. So we need to make a vector for that so we can make a line, right? And basically what we're going to do is kind of get that line, and we're going to essentially plot it, right? And then we're going to find when that line intersects this blue curve here. And then when you find the intersection point, that X intersection value, that's going to be that ductile to brittle transition temperature. So that's, basically what you have to do. But how you actually do it, whether you use a nested for loop or not, that part's up to you. For me personally, I thought it was best to use that nested for loop to solve everything. But you don't need to do that if you don't want to, or if you're struggling to kind of incorporate that on your own. You can use a different method, and that's fine. But in the end, I'm going to make a video after all of the memos are submitted, and I'll show you what I personally did. And just another note too, I'm going to be checking your code that you submit at the end of your memo. I'm going to make sure that in your code that you do have code for solving for that ductile to brittle transition temperature. So that'll be part of the grade. And also, for me, it was just convenient to solve for that transition temperature for all three materials. But in your memo, you should only be having a transition temperature for 1018 steel and 4140 steel. If we look at aluminum here, 6060 aluminum, there is no transition temperature. Now, for this data point here, there was a bit of a I don't want to say a mess up, but kind of a mess up for this group. Maybe they didn't get the sample on the test bed in time. You see it's kind of higher up than it should be. But aluminum doesn't have a transition temperature, so in the memo you should only present a transition temperature for 1018 steel and 4140 steel. All right, so that's memo 5. Again, that's due on November 29th. So make sure that you get started on that before the last date, because I know a lot of people, and I get it, but a lot of people start the memo on the very last date. You don't want to do that this time around for the data reduction. It's gonna, you're doing it on your own, so it's gonna take longer than usual, most likely. So get started on that if you haven't already. Kind of chip away at it every day if you can. And then your third memo, I'm almost done grading those. I'm gonna try to get them up by this weekend. So I just gotta grade through, I think for this class, I still need to grade through the results, discussion, and then the abstract. The abstract takes the longest to grade. And then I'll try to get the fourth memo graded. Hopefully I could get that graded during the break as well. Okay. And let's see what else to talk about. I think that's it. So today, last lecture. So we're gonna be doing the lecture today. We're gonna go on break. Once we come back from the break, that's gonna be when we do the 6th lab in person. And then after that, we're gonna have a little kind of review of the class and kind of prepare for the final. So I'll talk about the format for the final. I'll give you a little study guide as well. And then after that week, it's the actual final. Most likely, I'll give you a full day to work on that, and it's going to be online. All right, so the 6th lab. This is the Double Shear Lab. So this is what the setup is going to look like in the actual lab. So we have different fixtures on the MTS tensile testing machine. This top jaw here, it's going to be going down into this bottom jaw. We're going to have a little rod that goes through here. And as this pushes down, we're going to have shear failure right here and another shear failure right there. Okay. So we have 3 different rods like we do pretty often. We have 6061 T6 aluminum here. That's going to be color-coded green on the end. 1018 steel. And then we have copper. I think it's C40. Okay, copper 40 right here. So we're going to record all of the different diameters in 3 different sections, get the average. And then once we're done with the test, we're going to get the length. So that'll make more sense once we continue on here, but we're going to measure the length of the rods after the test for the part that's kind of in the center. Okay, we have different kind of pieces here to set up the test. So these 2 discs, they go in these slots here and over here. And then the centerpiece, well, obviously the centerpiece goes in the center. Okay, we're going to get the rod. We're going to slide it through the hole here. And you can see in this picture here, this centerpiece, it's already pushed down a bit. So that's, it's going to continue to go down. And that's how we're going to have the shear failure. So we're going to get this little piece in the very center here. And we're going to be measuring that length in the end because we're going to have a shear failure here and here. So just like with lab 4, we're going to apply a very small preload of 0.2 pounds. That's the goal, but if it's like 0.5 pounds, that's fine too. Okay, we're going to run the test, and it looks somewhat similar to a stress strain curve. I mean, this is load versus crosshead, but it looks pretty similar. So the crosshead position, if you guys don't know already, that's the position of the top jaw as it moves down. So it's the position of this. So it's going to start, we're going to zero it out, and once we run the test, that's going to go down. So that's the data that we're getting for the crosshead. So you see that the load is going to increase, and just like a stress strain curve, it's going to go down and it's going to fail or right around here. But what we are interested in for this lab is the shear strength. So we're going to look at that maximum load that we have, divide that by the cross-sectional area, and then we get our shear stress, which will be the shear strength. All right. We're going to export the data. In MATLAB, you'll use a function like max to get the maximum load, and then divide it by that cross-sectional area. Here's the test setup as the test is finished. So this part and this part here, they should both fall off, but sometimes it gets kind of stuck like this part here. It is totally sheared, but it kind of got stuck in this part here. So you're going to remove those, and then you'll get the very center portion here and record that length once we're done. And you're going to record that length once we're done to basically use that to calculate the bearing stress in the end. So we're going to calculate both the shear stress and the bearing stress in this experiment. Just like with lab 5, we're going to use this camera to take a picture of the fracture surface that we have. So this is that small little piece in the very center. We're going to take that and look at that shear surface that we have. So this looks like it's copper here, like a little brownish. So we're going to take a picture of that shear surface, and if it's a more ductile material, you're going to get more of this kind of smearing that we see here. And if it's a little more brittle, we're not going to have quite as much smearing. Okay, and this is because, as we continue to push this centerpiece down, if it's more ductile, it's going to be able to, to kind of smear more because it's not going to break as easily as something that's more of a brittle failure. So copper is going to be the most ductile for this experiment, so there's going to be quite a lot of smearing that goes on. Alright, so that's going to be the lab. That's what it's going to look like. It's a pretty quick lab from what I remember. It's been like 2 years now since I had this lab in person because of COVID. But from what I remember, it's like probably the fastest lab, to be honest. So kind of good. It's a good way to just finish off the semester by having a nice simple lab. Alright, so let's get started on the lecture. Alright, so I already wrote some stuff down just to kind of get it out of the way. So we're doing double shear once again. We have our 3 rods that we talked about. And we are going to subject it to that double shear. And we're going to do it 2 times. So we'll do one test. And basically we should set up the rod in a way where in our first test, that'll shear. And we're going to be left over with enough material that hasn't been affected. Or we can run our second test and subject that to shear as well. I'll talk about that for how we're going to set it up in the lab once we get to that. But we're doing it 2 times, or 2 different trials basically. So in the end, we're going to have 2 different graphs for the load versus the shear stress versus the crosshead position, which is what you see here. And we're also going to calculate the bearing stress, like I mentioned. We're not going to have any graphs for that, but we're going to calculate the bearing stress as well. All right, my iPad, the Bluetooth connection's been pretty shit lately. Let me reconnect. Hopefully it's okay. It was okay earlier this morning, but it's really laggy right now. Okay. Oh. It's still pretty bad. Okay. Sorry, we're gonna have to make do with this. Alright, so shear stress, this is probably a throwback to the very beginning of your solid mechanics class. So whether you already took that class or you took it this semester, it's probably in the very beginning that you talked about shear stress, or at least were first introduced to it. But the definition for that is the intensity of the internal force that we have, and it's going to act on a surface, and that's going to be parallel to that force. So in contrast, if we think about the first two labs, we had a tension test. So that force that we had, it was normal to the surface, okay? So we're looking at this force here, that's perpendicular or it's normal to this surface here and this surface down here. So for shear stress, we have our force here, and that's going to be parallel to our surface here. This kind of sketch is, imagine this is the rod that we're going to have, and this bar here is kind of one of those metal discs that we have. So we got a force going down, and this force is acting parallel to this surface here. So this part, this little left part here, that would shear off, and we would be left with two pieces in the end. So we would have this piece here and this piece here. So this drawing here, that's in single shear. What we are going to do in the lab is have double shear. So, I mean, same kind of thing. We just have two different surfaces that are going to be subjected to a shear force. So the formula for shear stress, well, it's a stress formula, right? So we get our shear force divided by the cross-sectional area. That's it. I'm sure everyone knows this, but you gotta say it. So the formula for shear stress, let's write it out. So our shear stress is going to be denoted by tau. And then V, that's going to be the shear force that we have. And then A sub V, that's the cross-sectional area. So I might say V, I might say F, I might say P, whatever. All of those, I just mean it, that's the load. So tau is our shear stress. V is our shear force. And then A sub V, that's our cross-sectional area for the rod. So, of course, just pi divided by 4 multiplied by the diameter squared. All right, so that's the formula for single shear, but we're doing double shear in this lab, so we got to modify this formula a little bit. Before we do that, I'm going to pull up a picture of what this double shear is going to look like. Here we are. So this is what our double shear is going to look like in the end. So we have this surface here, and we have a surface here. So in the end, you know, we have those two different surfaces that were subjected to a shear force, and they're both going to shear off. So in the end, we're left with 3 pieces. And once we're done with the test, we're going to measure that center piece, that length there. All right. Okay. So this is what it's going to look like. This is a little schematic here, just to kind of get a better idea. So we have this surface here that we talked about and this surface here. And we're going to use that to get our, we're going to measure that cross-sectional area here. Or really, we're going to measure the diameter, then calculate the cross-sectional area. And this part here, that's that kind of centerpiece that we looked at before. It's a little different in the actual lab, but the point is the same. We're going to be pushing down on the center. That's going to cause a shear force here and here, and it's going to break off. Okay. Go back here. Okay, so we have double shear, of course. So let's draw that little schematic again here. So we have our force going down, and that's going to result in those two different surfaces being subjected to a shear force. So A1 and A2, they're going to shear off. We got our double shear. So we need to modify our formula because we are in double shear now, not single shear. So we're going to have tau equals our shear force divided by now 2 multiplied by the cross-sectional area because we're in double shear. And I know this is all very simple, but we can rewrite this if you want for that cross-sectional area. All right, so that's a very simple formula. For us though, we want to look at the shear strength. So that's going to be, that's going to correspond to the maximum shear force that we have in the lab. So that's going to be one, we're actually failing. We're using engineering stress again, but the shear strength, that's going to be our maximum load divided by 2 times the cross-sectional area. Okay, so we'll box this because we're going to need that. And then the next thing we're going to talk about is the theoretical shear strength. So the theoretical shear strength, it was made from empirical formulas, and they're kind of crude approximations for what the shear strength is going to be. It's going to be a constant multiplied by the ultimate tensile strength for that specific material. So we're going to calculate that theoretical value and compare it to the experimental value like we often do. But I want you to keep in mind that approximation, that theoretical approximation, it's an approximation. So when you talk about your percent error, you should keep that in mind and discuss that, because it's not this great equation. It's an empirical approximation. So make sure you discuss that. Okay, so for aluminum and for copper, this equation is going to be 0.65 multiplied by the ultimate tensile strength for that material. And then for the steel, that's going to be 0.75 multiplied by the ultimate tensile strength. So just to reiterate again, these are approximations. It's not like this. It's not really this, theoretical derived equation. They're empirical formulas from testing that's been done. So when you talk about your percent error, again, just keep that in mind. It's not like this great, fantastic formula, right? And the last thing we're going to talk about now is the bearing stress. So once we're actually in the lab, there is more than just a shear stress that's going on. So the shear stress is the main form of stress that's going to occur in the lab. But if we're looking at this, once this crosshead is going down, yes, we're going to have shear stress. That's the main thing. But we're also going to have some bending that's going on because we have that transverse load that's going down. And we're also going to have some bearing stress that's going to occur because we have our rod here. And when our rod is placed inside of here, there is going to be bearing stress that's going to occur as well. Because we have a rod and that's sharing, there's some contact area that's shared between the rod and these 3 different metal discs that we saw earlier on. And because we have that shared area and there's a load being applied to that area, there's going to be bearing stress. So in the end, we're going to measure this length in the very center here. So we're looking at the bearing stress at that particular location in the center. So there's still bearing stress that's occurring basically from this point to this point. because all of that is shared area, but we're going to calculate the bearing stress that's occurring in the very center. Okay, let's go back here. And I'll give you a little, I don't know, graphic I made a while ago for this class, I don't know, a year and a half ago or something, just to visualize that a bit better. But before we do that, let's write out the formula for bearing stress. Okay, so the basic formula is going to be sigma b, that's our bearing stress, is equal to the force that we have. Of course, that's our, in this case, it's, it's the force that's going down on the rod there. And then a sub b, that is that shared area of contact. So let's rewrite this for our lab. That's going to be our force. Our force divided by L sub m. So L sub m is the length of the rod that's in that middle section, and d is the diameter of the rod. All right, so we're going to need this as well. So let's take a look at this little graphic. Let me go out of there. Okay, that's good enough. So put this over here. We have our rod here, and we have the 3 different metal discs that we have in the experiment. Not a great job. This middle one I think is a lot shorter, but whatever. It's the same kind of thing. We got a rod, our 3 metal discs. We're pushing down on this centerpiece. We're gonna have shear here and shear right here. So this bearing stress that we have this rod here, and their shared area with the rod with those 3 metal discs starting from this edge, going all the way over to this edge here. But in the end, we're just going to calculate the bearing stress for this kind of center portion here. You can't see the cuts right now for the 3 different discs that we have, but basically we're calculating the bearing stress for the length of the rod, kind of, around here. And that's going to be equal to that length of the rod here multiplied by the diameter of the rod. Right? So basic visualization. Oh, here's a better one. So we're looking at the length from here to here multiplied by this diameter. That's going to be the bearing stress in the center portion of the rod. Okay, so that's it, right? That's it for this lecture. It's pretty basic. We're just looking at the shear stress, double shear, and we're looking at the bearing stress. We'll make a plot for the shear stress versus the crosshead position for all 3 materials. We're going to have 2 trials, so we're going to have two graphs, each graph 3 curves on it. Compare the theoretical shear stress to the experimental shear stress. Keep in mind the theoretical formulas are very crude approximations, and we'll calculate the bearing stress as well. So that's what you're going to be doing for the memo, and that's it for today. So keep in mind your 5th memo, that's due on November 29th. Make sure you get started on that if you haven't already. Seriously, get started on it, because you are going to have a really bad day if you get started on that on the very last day. So I still hope you guys, take time during the break to chill out a bit. Hopefully you have time to do that and you don't have projects, although I kind of get a feeling you probably do. But still, take some time. relax, and you know, just chip away at this if you haven't already for the fifth memo. Okay, I'll be able to answer some questions to you if you have any over the break. Don't expect me to reply right away. You know, I'll be doing stuff too, right? But I will still be available to
Thank
help
you for that, Patrick.
if you need help. Yeah. Okay, so that's all I have for today. So I'll see you guys after the break. Remember, once we're done with the break, we're doing our sixth lab in person.
You too, Patrick. Have a good break.
All right, thanks. You too.
Thanks. Have a good Thanksgiving.
Thanks. You too. Any questions?